Well, good evening. Aloha. Thank you all for coming this evening. We have Doug McCarter coming to talk this evening about rock wars that we can win with silicon. And I met Doug a couple months ago at a meeting in Los Angeles. Excuse me. And he gave a very interesting talk, and I thought it would be interesting for him to present here. So we invited him here to talk about, he's been working with single crystal silicon. So you know the stuff that's in these computers that makes our computer chips work, it's actually made as a big single crystal, sort of, he's going to tell you about it, sort of the shape of a salami. And it crystallizes into a single crystal, pure silicon. And they dice it to make wafers for computers and stuff. Doug has been for many, many years using this material to make things, to make instruments, parts of instruments, mirrors, all kinds of things. And he'll be telling you about that. And the benefits of using this material in space. So without any delay, I think I'm going to give you this little.
Good evening, ladies and gentlemen of Pukalani, Maui. I love all these smiling faces. Makes me calm down quite a bit. I get very intense and passionate about single crystal silicon. Been studying a very long time. We've been very much in the progress and the limelight of using single crystal silicon for optics and structures. With rock wars, we can win with silicon. It's a interesting thing to find out and study why we have trouble seeing the cold asteroids. They're cold to begin with, but why do we worry? Because the Aerospace Corporation has determined it's only 1 in 1 trillion chance that a rock would fall on a person and kill them. As you see, it's not the rock falling on you to kill you. It's a much bigger problem called an explosion. Where are we? Well, there's the sun. We're at 10 o'clock. See the red? That's the Earth. I'd rather be here to be away from the asteroids, but then we'd be disintegrated by the sun. So we just deal with our life as we have it on planet Earth, where we're at. And what's been happening more and more frequently is that more and more asteroids, and I'll be calling the rocks asteroids, and they have lots of names, whether it's a planetoid or bolide as it explodes or a surviving meteorite. I'm not going to be saying a lot of different nomenclature. I'm going to either say rock or asteroid, but it's the same thing. What's happening, even under our satellites, we're having rocks come flying through. And what's really disturbing is we've been seeing a lot of them on the way out. After they came by, missed us, thank God. But still, we have to be able to identify these things it's called detecting a rock, or detecting the asteroids. NASA said this one was about 150 foot. It would have flattened 825 square miles, just like the event in Russia back in 1908. And they said, well, that size asteroid statistically wouldn't hit the Earth but every 100 years. Well, we're really close to that. And I don't want to be close to that. I don't think it's a good idea to ignore this. And they said, well, we'll just move the satellites out of the way and they can go by and they're not going to hit us. Okay, next slide. Well, actually, micrometeorites are striking all the time, and they're doing damage, about $100 million a year to our satellites. The space trash and the rocks coming are doing damage, but they're small, and they're nice, beautiful shooting stars as they burn up in the sky. What we've got to worry about is the macrometeorite. That's not even a word in the dictionary. I'll put that in there because you need to understand it's a follow-on of the small is the large. How do we know this? Well, unseen recorded events. NASA did not see any of these events, but they're courtesy of Nuclear Test Ban Treaty Organization. They're monitoring, looking for people setting off nuclear bombs, which is very, a lot of energy. An explosion is energy, like a hand grenade, a nuclear bomb, or an asteroid is the same thing. It's the energy from ocean coming in at 20,000 miles per second or more, up to 200 miles per second, depending on the size of the rock, and all of that energy exploding. Hiroshima bomb was 15 kilotons and did some damage. It hit the city. Luckily, none of these have hit a city since 2000, but we don't want it to hit a city, ever. We don't want to recover. We don't want to rebuild a city. And if you lost one city, the whole global economy would collapse from panic. You have to understand, it's not just losing London. You can't rebuild London. You can't replace London, or you can't replace Paris. You can't. It's the panic that would ensue of being out of control, thinking we have no control over seeing these rocks coming. We can't do anything about them if they're coming. And realizing that, you should realize it now. We have to do something about it, and I think I have a plan. Looking at the amount of kilotons, it's incredible that the amount of kilotons that were picked up. And most of them hit in the ocean because we have so much water, which is very protective of us, which is good. But what was really interesting, when the investigators went to a particular sea and found where the explosion happened, and they went underwater, and they actually did see a crater underwater, there was other craters around it that we had never known about that's happened through history. It's a really great book, is Scattered Dap and Remember. It talks about how the Earth has been almost annihilated 7 times by volcanoes and asteroids and solar flares and different things. But asteroids or rocks is the only preventable natural catastrophe that we can actually deter and avoid. On here is the Russian explosion, which I'll show you a little more later, 20 kilotons. Luckily, it was out of the city, over in the woods, and you'll see the damage it caused from Chelyabinsk and a couple of other cities. And the children, they rushed to the windows to see what the flash was about, and the sonic power from the rock miles away blew up in their face, and 1,200 of them went to the hospital. Okay. And fortunately, a lot of asteroids come in at a obtuse angle, acute angle. If it came obtuse and came straight down, the damage would be even worse. And I think maybe there is a difference between an atomic bomb and a rock in that way, because I think it was dropped straight. But still, there's 3 cities, millions of dollars of damage, over 1,200 injuries, and the surviving meteorite or rock was picked up out of a cold, icy lake, and it was still the size of a Volkswagen. And it's still, so back to the rock can't hit you in the head and kill you. Well, I don't know if that's true, because if we're in a city, that surviving rock is still going to be going, even though if the explosion doesn't kill you, that rock is going to do something to somebody. Thank you. Well, let's just evacuate a city. Let's say we can see a rock is coming. I live in Houston, Texas. This is courtesy of the Houston Chronicle. Hurricane Rita didn't hit Houston, but they're predicted at the last minute, it's going to come to Houston. So everybody tried to rush out of the city the same day. But what happened, it stalled the traffic. No one went anywhere. And actually 100 people died in one day trying to escape of water. Could you imagine if we say an exploding rock's coming tomorrow? Let's get out of town. 67 elderly died, and they tried to take a makeshift school bus and get them out of town. And it caught on fire, and they all died. And the rest of the people killed each other violently, trying to get out of the city. They just lost their mind. We don't want that to happen. This just shouldn't happen. Okay. Well, so I started thinking. I was teaching a class, or talking in an optics class, about how we can take geoscience, marry it with astroscience, and take the infrared and turn around and see asteroids. And I was thinking about this because what they do, the geoscientists, they have infrared on the satellites, and they're looking down at a place that has malaria, so they can find the mosquitoes. Everything has a color in infrared. They can find the mosquitoes. Better than that, they find the larvae. So therefore, you go and kill the larvae, you don't have to spray a bunch of herbicides and pesticides and try to kill the mosquitoes themselves. You stop it at the root. Well, the same thing I'm thinking. We find these cold rocks. We can control these rocks if we can get up there. And I have a way to get up there. then I'm going to propose to go and move these into a safe orbit. But why can't we see them? I don't see many people in here with glasses on, but if I forget my glasses, there's a little trick my wife taught me. You take a cone angle, you make a big hole and a very small hole, and you can look it through your eyes, and you can look on the paper, and you see a shadow, and you can read without your glasses. You can actually read. Because the starlight, the light in the room, it overcomes the ability to read. So we have to get rid of starlight. Did you know that if you stepped out 10 million miles away from the Earth and look back, it doesn't exist? All you see is the sun. Why? Because it's bright. And the sun, the Earth's not dim. It's not considered dim. It's 0.3 out of a scale to 1.0. It's 0.3. It's not dim, but it's too much starlight. So our problem here is not resolution, it's contrast. We're going to think about the Kepler telescope. It was a wonderful idea. It's named out of an astronomer who was alive the same time as Galileo. And NASA refused to do the Kepler telescope 7 times. The proposal went up. And finally, in the 1990s, we had the Kepler telescope, and we saw the first exoplanet. And in October of last year, the Kepler telescope was turned off. So we need to get something else up there. Stray light. Stray light occurs with the way you make your telescopes, the way you make your equipment, and anything you would let interfere with your vision. Speckle is like atmospheric disturbance, which you don't have in space. So we want to go to space with our drones, but you'll still have some delay. You can't ever get rid of all the speckle, but you can reduce it. One of the most important things I've found as a manufacturer is the scatter from bad optics, no matter what the material is. What's happening is they have scratch dig tolerance, which is how wide and how long a scratch could be. Well, that's fine, but when they go clean and polish and get ready to use the optics, they scratch them, and then they still use them. Well, what we started doing is starting using a pristine silicon crystal, silicon, with no scratches, no sleeks is what it's called. And now we have a pristine optic that can see cold asteroids. Infrared. You see the Hubble telescope, the visible on the top left, it does a great job in the visible. But look what happens in infrared, how much more you can see. We're going to use the infrared for this mission. Everything has an infrared signal. All objects have an infrared number. Everything in this room, everything that's changed, the curtains, the carpet is different, everything's different. So you start a library of understanding and studying what are we looking at. The first exoplanet in the 1990s was actually found with the Kepler telescope I was talking to you about. And what it was a shadow coming across the star. Because what he did, like I did, with my hand, I made a very small hole, a chronograph, in the telescope, and then you watch for shadows. It was a really great idea. And the cold asteroid in the visible is different than in the infrared. The materials you use is very important and it's very neglected. I'm not going to say we don't need the JPL Neowise telescope. We do. It'll do a function, but it's very limited. Very, very limited. And why is it limited? They do an excellent job of polishing, coating, cleaning. The problem comes when the temperature changes. I think it's something a lot of people don't think about. They didn't even know. We have problems launching aluminum. I'll show you later that it bends on launch. It moves. It's very cheap. It moves. It's easy to manufacture. It moves quickly. But this is not good for this mission. It's good for something else. Because if you start having blur, like the bottom screen, you're going to start having trouble really pinpointing exactly where your rock is at. NASA even has reported in writing that they think asteroids disappear, and then all of a sudden they come back again. And I was at Mirror Tech Days talking about this, and I said, maybe they have a cloaking device. Is that what you think it is? They do disappear? No, they don't disappear. Your optics, and this is 20 degrees temperature change. Like a telescope. I bought an outdoor backyard telescope, and it says on there, please allow 1.5 hours. If you take it outside, that it's nothing wrong with the telescope, don't call us. Let it have its time at 1.5 hours. In 1.5 hours, that asteroid's going to be gone. But what happens with single crystal silicon, we're designing all silicon telescopes we've been designing for a while. And the blur report, it has to stay in that circle. And that's a 20-degree temperature change. Silicon can go from minus 170 cold, okay, to 500 degrees C, like on Venus, and never get out of that circle. Go ahead. Well, how do we know what happens at launch? No one's done this test. So my great, late great Frank Anthony from Bell Laboratories, he came to work with me on the space-based laser program. We designed this cantilever test. And what we did, we wanted the optics to move on launch. So he said, let's make it cantilevered over so that it wants to move. And we used our glass FRIT bonding that we developed at McCarter. We took 8 pieces, bonded them together. They machined the faces, and the diamond turned the faces. Same thing, we made an aluminum monolithic counterpart. He said, well, let's launch it and see what happens. Well, there's your modes. You have your launch. Your boost is your second one. You know, you've seen the rocket, and then they boost with the power, and then the orbiting in the cold, and then the reentry. All of those 4 modes of launch and reentry. And the aluminum sample actually bent like it's showing and stayed bent because it's metal. And single crystal silicon didn't bend to begin with, but if it did bend, single crystal silicon comes back. It's a bimetal, it's a metalloid. On the periodic table, it's right in between ductile and brittle. It's right there at the edge. It's one of the only materials that you can bend and let go and it comes back. And the structure, the atomic structure, it helps me anyway, understand why. Why would silicon be so great? Why do we use it in high energy lasers? Why is it the best for the interceptors, telescopes? And why in the space would be best for never being lost in space? It's the cubic structure. It's like the diamond cubic structure of the single crystal silicon. There's 3 predominant planes. If you have that bull, Dr. Gary was talking about, it's a cylinder, and we cut it this way, it's a 100 plane. If we go at 54.7 degrees, I'm hitting my 111 plane, which you'll see why that's a good plane to remember. If I come this way, it's 110. And those are our 3 predominant planes that we study. And as he mentioned, that's what the wafers are made from. If you take that wafer, you can bend that wafer without breaking it. Now, the thinness determines how far you can bend it. But I have pictures. It can bend all the way down, and it'll come all the way back. But it has to not have any subsurface damage, and that's where we got a patent on getting that out of our parts. It's grown in a Tchaikovsky puller, where it's a bunch of silicon they remelted in a quartz crucible while it's spinning. And it's like making candy. You take your candy, you get it started, and you start pulling candy, rock candy. And how fast you pull it is how skinny or how big a diameter you have. What's amazing is you think that it's a brittle material, but look how small the neck is. That's very, very small, and that holds hundreds and hundreds of pounds of weight as it's pulling. That's the only thing holding it. It's while the molten silicon is spinning and it's pulling up, even bulls this big, you have a very small neck on it. And it doesn't just snap and break back down in the mold. So it's very deceptive. Single crystal silicon, if you design this in compression, it's stronger than stainless steel. On the hardness level, it's 48 to 52 Rockwell C, and 4140 heat treat steel, it's only 28 to 32 Rockwell C. It's a very wonderful material to build with. Thank you. Our technology up to 1998 hasn't changed very much. I actually got to visit the Super Silicon Institute in Japan when they built this machine, and that was the biggest at its time. They haven't gotten much bigger, maybe 450, 460, a little bit more millimeter. So what we did at McCarter, we decided with our instruction of our scientists to actually learn how to bond it all together to make something as big as this room. Why is silicon different? It's these material properties. Everything has properties. Everything has mechanical properties. They pretty much stay the same. So I'm just kind of talking mainly about the thermal properties because we're talking about temperature changes. But the one thing I'd like to point out is mass deflection factor. Beryllium is the stiffest, and it won't deflect as much. And I always thought, oh, that's the best material to use for, optics and structures because it won't move. That's not a good idea. It's called a spring merit factor. You need to be able to spring and come back. And all you're doing is causing a big headache when you have something too hard and too stiff. The thermal diffusivity is the key in silicon when it gets to space. It takes off and leaves everything. And what that is, it means when there's any temperature change from 1 degree to 500 degrees C to 1,000 degrees, this is how fast that thermal transport goes through the silicon. This is why on high energy lasers we don't cool them. It just goes through it. Steady state, transit state, whether it's moving in temperature, your expansion coefficient, your conductivity, it's the most highest material, even more than copper, in space. Now, here on Earth, copper's better for conductivity, because that's why we use it in our electrical wiring. We don't use silicon. But in space, this is what we want. Okay. Back to the planes. I know it's a little bit strange to think about, but not really. It's a square. It's a square. When they grow the bull, you can see the lines. It makes it real easy. I should have brought one. You can see the lines. There's 4 lines 90 degrees apart. It's the growth nodes. And what you could do is you can take a X-ray and you can actually see inside the crystal and mark it. And that's what they do in the computer world. And they put a little notch where a node is. Now you can know what you're doing, what you're dealing with. And that's what we do. We'll notch where one of the mother nodes are, and we can know where we're at. So what happens when you have flash heat or flash cold? There's a lot of materials like in this room. I could put an aluminum bench here, and you may see it move. The temperature of the room moves some, and that's fine. But what if you're in a very hostile environment? Very hostile. Like space is very hostile. You don't realize how hostile it is. But what if happens with a high energy laser? What if you have a real thin sheet of any material, like zero door glass? It takes 1.5 minutes for that thermal diffusivity to reach equilibrization. 1.5 minutes. Your rock is going up to 200 miles per second, and you're waiting 1.5 minutes. And then, okay, that's back on again, and where did it go? And single crystal silicon is less than 1/2 of a second. It's 0.5 at the most of 1 second. It's sub-second. And submicron movement, a growth, and sub-second thermal equilibrization. It's very unique material. So looking at how do you build telescopes. This is a Cassegrain telescope. We didn't invent telescopes. We didn't invent the Cassegrain. Everybody uses Cassegrain. This is a 4 mirror. What we invented is how we make it out of silicon, how we mount it, and how we make adjustments to it. Let's look at the spider. The spider's on the left, and that seems to be like it has legs on it. So that's the scariest part of a brittle material. You think a long extension like a diving board, you want to avoid cantilever. Go ahead. Well, back when we did our test, we did some FEA, which is finite element analysis. That works real good on paper, but to really do it is more important, to actually do the test. So we did both. And what we found out is it's under the 1 KSI stress level, which is, for any glass or brittle components, that's an acceptable level. If it was worse, we wouldn't be able to use it, and it wouldn't survive anyway. So what happened? That's acceleration. Let's look at a different mode of vibration. Go ahead. Displacement. When you're moving, how much is it going to move with you? Did you know it's called spacecraft slew and spacecraft acquisition? When spacecraft stops in space, everything inside wants to keep moving. So it's kind of a phenomenal thing. But what's wonderful about silicon, you don't lose your optics. You've always heard about lost in space. Like, you can see, and all of a sudden it's blind, and all of a sudden it comes back on again. And I never knew what's going on. Why don't they fix that? I don't want to be blind in space, but they're not using single crystal silicon. Look how small it moves. It's submicron movement. So sub-second thermal equilibrization and submicron movement going from Earth to launch up to cryo. And even if we went to 500 degrees of Venus, we've proven it at Goddard Space Flight Center, it doesn't move beyond the submicron movement. So when you're in cold, how's it going to react? The great James Webb Space Telescope they're building out of beryllium, they're having to make it crooked on the Earth. I don't know if you know that. So that when it gets to space, they're hoping it will be in focus. Because it moves so much when it goes to space. It's called cryofiguring. You don't need to spend money on that with single crystal silicon. What you have is what you get. It's going to stay. You can rely on it. You're not going to be lost in space. You're not going to lose your rocks you're watching. You're not going to lose anything you're watching. Go ahead. Coming back. All the optics go off and you're lost in space. As it re-enters the Earth, it does not move. Coming back. Well, how do we know what's going to happen? So we made a lightweight mirror, first lightweight mirror at Goddard Space Flight Center, and they put it in a chamber. What the strangest thing is, they put aluminum fingers to hold the mirror together, to hold it. And what happened, that pinches, because aluminum goes crazy when it goes from room temperature to cold, but they use aluminum all the time. All the time. So I finally talked them out of later. I said, let me make you some silicon fingers. Oh, he can't make silicon in structures. I said, we've been making silicon in structures before I made optics. From 1988 to 93, when TRW and the Air Force came to me, all we made was structures. Maybe we can't make silicon structures. Just make it and test it. But the wonderful thing about the difference of silicon is from room temperature to space, it never lost focus. If you understand these numbers, which I don't know if I do, they have to explain it to me, but so I have scientists who work for me. It doesn't lose its focus. And I'll go back to the beryllium. So it's not in focus when it launches, because they're hoping it will be when it's cold. Silicon is the only thing that you can watch and actually view and keep looking why it's going to cold and why it's coming back. It's a very unique material, but it's been proven by Goddard Space Flight Center and NASA and Space Qualified. Very first samples we did, we had to make some coupons, made silicon coupons. Some of them are coated, some of them are uncoated. Some of them have a glass FRIT bond joint right down the middle. We put them in these trays, and they went up for supposed to have been a 9-month study. And unfortunately, our brothers and sisters that lost their lives in Colombia coming down, and they were standing up there for about 4 years, all of our samples. The McCarter silicon samples were the only ones that survived without any changes. There was no changes. Even if a micrometeorite hit a sample, which it did, the single crystal silicon will cleave at that 111 plane, and it stayed in focus. So you don't lose your optic, like it doesn't shatter like your windshield with a big rock hitting it. It actually cleaves. Go ahead. Oh, I'm sorry, back up, please. I need to point out some numbers. The sunny side, which is called the RAM and anti-RAM. RAM is towards the sun. This was like 4 years of RAM and anti-RAM. It gets to be 185 degrees in space. That's really hot up there, but that's facing the sun. And on the dark side, it drops down to minus 386 degrees. I'm talking in Fahrenheit. So what's that telling me? If you have a mirror that's staying in space and the sun is hot and the back is cold, if you don't have single crystal silicon, it's going to bow. No matter if you made the beryllium be focused on the Earth and cryocycle it and get it ready, cryofigure it so it's in focus, what are you going to do when it's hitting the sun? And I'm not talking 5 degrees, 20 degrees, So there are hundreds of degrees of difference from the hot side of a mirror to the cold side of a mirror. So they have coolers, they have heat pipes, they have algorithms, they have motors, and all this stuff that has to go up to space. This is why we can build what I want to build with single crystal silicon. We don't need any of that. So we can make a compact system, as I will be showing you in a few minutes. And there it is. Super compact. The space drone concept that we have, maybe as wide as this room, by this wide, is all you need. And it's self-supporting. You don't need the cylinders. You don't need gases. You don't need ion thrusters. You have silicon power thrusters, high-energy lasers by silicon power. We don't need the giant panels of silicon. You know, everybody knows there's giant silicon panels for powering spacecraft, instrumentation and so forth. We need a lot of energy. So the parabolic conical collectors is what we want to put on the drones. And we'll be able to have so much power, we're going to be dumping power. We'll be scraping power off and dumping it because it's too much power. We just had a wonderful report from the X-37B, which is normally a classified closed program. I'm able and released by Marshall Space Flight Center to use my information because I'm a commercial company and it's my test that they agreed to test. What we did is we took single crystal silicon, took our glass FRIT powder that I'll be showing you we use, and we coated the panels. And what happened is that it stops all the damage from space onto the system. So single crystal silicon, glass FRIT powder, and the 39 nickel iron are the three components of our technology. I'll be showing you that's what we're depending on. Well, actually, you have a targeting laser at the bottom. You're going to have a very small 8-inch primary, 4-mirror wide view, and the binocular telescope at 8-inch. Very small. You don't have to be big. This is the whole crazy thing. You're going to start letting in too much light. How are you going to see anything? I couldn't see you if there's a giant spotlight in my face. Okay. Well, here's our technology. It's very basic. 3 parts. Super finishing, which we had a patent on, which is run out now, and you're welcome to use it. The metal insert, I'll never tell you how to do this. And the FRIT bonding, we'll never tell you how to do that. But what we're doing is we're making modular components to where you can take that mirror and bolt it on and it's already lined up. And that's a wonderful thing. That's a wonderful thing, because in a battlefield, if you had a coating burn up off of a mirror, you can pop off a mirror and put another one on. Existing technology, it's dead for months. You'll be lucky to get the mirror out. So it's a wonderful thing. And the mirror itself, I can make those and put them on the shelf. NASA has proven through my mirror, first mirror I made to them, and they've checked it for 6 years and 6 years again. It still has never moved. It's their incoming inspection standard. It's a lightweight mirror, very basic, very simple, single crystal silicon. The only bad thing is they don't need lots of them because it doesn't change. So I'll have to go find other work. Okay. Back to the first machining with no subsurface damage. It's very, very, very important to get the damage. You have a perfect cubic structure with no damage in it. It's called zero defect, ZD. And what happens, you machine it and you mess with it and you damage it. Well, we learned how to get the damage out that we put in. But what's interesting about this picture is that we have holes in this undulator bar. And you can actually make these active optics. And the wonderful, they have different materials used and make adaptive optics because they have to make them work. We do ours so we can use it. And then we let go, it goes back to the original place it was. Go ahead. We bond together. That's 8 pieces bonded together, the glass FRIT bonding, and then we don't find any discontinuity in our manufacturing process. So, customers started saying, yeah, but what if this happened, or what would happen if this exposure? So what's happened is a wonderful thing. We have a battery of 42 independent third-party tests on our product and our manufacturing abilities. All their questions and our papers that I write, it's all about that, answering their questions. And it makes it all so much clearer. And you can download my papers, go on to McCarterET.com and get the papers and read them for yourself. Basically, of course, a lot of people bond things together. They use epoxies, they use solders, they use tin foil, glues. They try to bond it together just by itself and cause all kind of strain. But if you take the part and get all the no cracks and no subsurface damage, then bond it together with the glass powder that has the same CTE as the silicon, then it's going to go together and react monolithically, which would be like it's never bonded ever. And then the direct attachments are very unique. 3 points determine a plane. So we just made it to where you can pop your mirror on, pop your mirror off, and on the outside have automatic alignment devices. So you put your system together and you're turning mirrors. It makes it so much easier. I found out when I started learning optics that people spend more money aligning optics than making the optics. It was incredible. It was an incredible waste of money. You can make any shape, any parabolas, hyperbolas, tapers. You can make any shape and get the damage out because it's just a process. Doing light weighting is very economical. It's feasible. And we can do it in mass production very easy because you can make each piece, put it on the shelf, and it doesn't move. And then you can do the final adjustments if you get your final designs. But we just do a saddle across, and we frit bond the meniscus in the middle picture to the saddling, and then we do our finish diamond turning on the other side. What was really interesting about the frit bonding is that protects that mirror indirectly from space radiation or other types of cold X-rays and other problems. So my proposed scenario is that initially we have 48 silicon space mobile drones. You have L1 orbit, L2 a little further, and L3. And to be able to position around and protect the Earth, I would estimate there would be 48 of the smaller drones. I'd like to retrofit large queen bee drones, I call them, to be available for very large asteroids, and then have the working drones to start working on getting off the space trash and cut it up and get it off of the orbits. What we have, especially with the space cubes going up, and they just have a very short life, then all of a sudden they're a projectile. So all in space, all the satellites are dodging and avoiding trash. Ever since the very first launch of Sputnik, it finally came down from orbital debris decades later. But the other ones are still there, and all this trash is there. And any explosions, which like the batteries explode in a satellite, they have issues. They have collisions that happen that actually do have causes more man-made debris. That debris falls to the Earth. If you Google space debris, you'll see giant pieces that have missed people in houses and fallen next to them sometime. You can just look at all the trash that's falling that can't burn up. It's too big. We need to cut it up. And that'd be a great practice as we're waiting to be able to attack a rocket's coming. But to attack a rocket's coming, we need your help, which you have here on the mountain. And I think that Atlas will be able to tell us where it is. Pan-STAR will be able to tell us there's a danger. And with these drones, they can actually zoom in and go to work. And I don't mean to blow up a rock. You don't want more rocks. You want the Regulus heats up. It's been proven. It was proven by, let's see, I always forget his name, Marco De Ballo of the Cote d'Azur Observatory in 2014. The carbon rock or asteroid is the darkest, it's the hardest to see, and it's got the most regolith on it, but it can heat up really hot, and you can move that rock with pulse lasers. You can move your stuff around, not just cut up the trash with pulse lasers and continuous lasing, but you want to drive it, you want to control it, you don't want to make problems worse. Well, how would you do that? When I proposed this to different organizations in the country, not to say who and where and which, all I'm saying is saying, wow, it takes systems engineering and take a lot of people. It would take a whole separate maybe Space Force or a whole separate division and then to do this because that's a lot of work. And I was thinking that's probably true too. But at the same time, I just think about my grandkids, how wonderful they are on the computers and their games. And my great-grandkids, they'll probably be even more inept and able to do this, to be able to sit here and take care of business. So I hope this goes through. It looks like it's going to. We've got a lot of things to do, a lot of work to do, but I'm definitely not going to sit back and just say, let's evacuate. Is there any questions?
Thank you.
Okay. Yes, sir.
It looks to me like this has 1,000 different uses here on Earth and in space. I was thinking the other day about gravity and with all the space junk, and if we had the power and the photons to make something heavier so that we could guide it down out of space. But this is just amazing. It's funny because you look at it and you say, why haven't we been using this for about 25 years?
Yes, sir. Awesome. Yes, sir. Yes, sir.
Two questions. Thank you very much for the talk. It's fascinating stuff.
Thank you.
First question is, why do you think that the world's government pays so little attention to a problem that can cause a mass extinction event? How come the world governments pay so little attention to this? It seems like we don't hear about any concerted efforts to detect these things and develop methods for diverting them off of a collision course with Earth. So why do the governments ignore it? And the second question I have for you is just your opinion. What would happen if we had an event similar to or worse than the Carrington event of 1859? What would happen to all the microchips on this planet? Those are my questions.
Be fried. Yes, sir.
Right, yes.
Could you repeat the question so the people in the virtual audience can hear?
Okay. Well, first, I understand you to say that why aren't the other countries? Why not all countries interested in doing something about this problem? Why are they ignoring it? There are some countries. There's a few, but what they're focusing in on is mining asteroids, being able to control them and make money, trillions of dollars. It's all about the dollar. They don't realize how many dollars they're going to lose if we lose a city. They'll lose all the equity they have. The economy will collapse. They don't realize it. I don't think they're realizing mankind sometimes, I don't know what it is that makes it where we get blinders, maybe. And I would hope they would just take the blinders off and see the value of prediction and keeping prediction and prevention. And then, yes, if we had an event like that you were talking about, and we lost electronics, that'd be a global disaster right there. Very, very horrible.
So
Very
you
horrible.
agree that is a possibility.
Oh, yes, sir.
All the microchips.
Yes, sir.
Be just completely
Yes, sir.
rendered useless
Right.
by
The size.
pathogen.
Yeah, by the size of the asteroid. And again, the small to medium-sized asteroids are the ones we're blind to. We see 95% of the large ones. NASA has seen them and clocked them and categorized them. But the 5% is still there. One of the 5% we're in bad, bad trouble. I mean, worse trouble than losing our money. But I don't want any more children hurt. That just irked me, thinking, we let this happen. Let's don't let this happen. And then the other gentleman, his comment was, he sees a lot of uses for this technology. And that's a wonderful statement. Yes, sir.
Just a practical question for those of us in the audience who like big mirrors.
Mm-hmm.
So if you cleave on the 111 axis, you'll have something with higher elastic modulus, suggesting you can have a lower aerial density in your mirror.
Yes.
So do you care how you cut these, whether it's 100 or 110, or you're doing a FRIT bonding, putting it together?
Okay. For making large meter class mirrors, should I care to use the 111 with the higher modulus?
Does it affect your FRIT bond?
No, it doesn't affect the FRIT bond at all.
Because you want the 111.
Right. The 111 I only need on small aerial density or small aspect ratio length to size, like a leg. I'd use my 111. But if I'm making a big mirrors like we did in space-based laser integration experiment, we used the whole bull. We used the whole length, the 110 plane. It is plenty strong.
But it has lower elastic modulus. So
But it doesn't show up. See, in the paper that I wrote, the anisotropic material, isotropic behavior of an anisotropic material, single crystal silicon, SPIE, it explains that under loads you will see nothing. Even though the hardness has a slight difference, the modulus has a slight difference, the reaction to loads is isotropic, no matter what plane you're on. If I want a cantilevered strength, I would use the 111 plane. But if you think about that too, wood is a brittle material. So if you took a pencil and you broke it in half, anybody could break it in half. I can't break it again. So what happens with, in design principles with brittle materials, you want to reduce your length for small diameter to length. If you follow what I'm saying? And it's just very practical design rules that you use with single crystal silicon. And that's a failure that mechanical designers have been having for decades. They keep trying to design like a ductile metal material. Those principles, you can't use that. You have to really change your mind and use the brittle material design rules. Thank you, Joe. Any more questions?
thank you all.
Thank you. Thank you. Appreciate it.